I don't want to overstate the significance of this paper, but I think it's pretty darn exciting, and I want to tell you why. So this isn't going to be even trying to summarize this whole paper. It's 32 pages long. I've only skimmed it, and there's so much for me to learn in it. But I do think that if we break up the stages of quantum machine learning from the beginning, from the birthplace to now, it can be attributed to three different kind of stages, and from a quantum linear algebra perspective. And I feel like this paper ushers in a new age for quantum machine learning, specifically quantum linear algebra, that is very interesting. So the quantum machine learning could usually be attributed to starting with the HHL algorithm. And the HHL algorithm wasn't explicitly a quantum machine learning algorithm, it was actually it was a quantum algorithm to solve linear systems of equations. And this HHL algorithm rested upon the single condition that the matrix that forms once you represent all of these systems of equations is sparse. And that condition is what ushered in a whole new set of these primitive quantum machine learning algorithms that used in some parts the ideas from the HHL algorithm and thereby adopted the inherent condition that the matrix be sparse, that the linear algebra that it operates over. So so yeah, so but the problem that that presented was that when classical machine learning started to emerge, it was very clear that the matrices that people were dealing with was not sparse at all. A sparse matrix is one with a lot of zeros, but ML involves a lot of dense matrices. And but the one thing going for it is that these matrices, and they talk about all of this here, is that they have a good low rank approximation. And what that allows you to do is that inspires a whole new age, the second stage of quantum machine learning, which depended on QRAM. And QRAM is generally this approach to load different state vectors and that encode different vectors of your data and in a quantum RAM basically. And you fetch this quantum RAM, which is a pre-processing, and to do your actual quantum algorithm. And there's been so many of those quantum machine learning algorithms, which they were dubbed as, that actually proved to have theoretical speedups. Many of them meaning singular value decomposition, classification using quantum support vector machines, regression. There was quantum clustering. There was this whole suite of quantum machine learning algorithms that emerged from the development of QRAM. But there did emerge kind of a problem with that, right? So, although it's still a very active area of research, and there is a quantum algorithm retaining an eighth power polynomial speedup that uses QRAMs, there remained a problem. And the problem usually kind of nullified the actual speedups of the algorithm because the end-to-end analysis of it didn't provide that much speedup. Why is that? Because that pre-processing, the actual making that quantum circuit for the QRAM requires a lot of not only circuit size but also circuit depth, and querying so many data vectors is prohibitively large computationally, and it kind of just choked the quantum speedup that you get from the actual algorithm. So this paper, why I find it so exciting is that it presents an alternative paradigm to approach quantum linear algebra, and it's distinct from the prior conditions that were dependent on sparse matrices, number one, and number two on low rank approximations, on these matrices having good low rank approximations. So yeah, so they say that, quote, the main conceptual contribution of our work, and I can probably pull this up right here. They say that the main conceptual contribution of our work is to introduce subspace states, which are quantum states encoding subspaces of arbitrary dimension. And I found this really interesting because I felt like this was a complete paradigm shift on how we view quantum state preparation and quantum computation of certain data vectors to this day. Instead of viewing them as vectors, they present two actually efficient methods to represent whole subspaces of whatever Hilbert space you're operating under within a quantum state. And that is really interesting. I still have so much to dig into it, but I'm already very amused. And not only that, but they oh yeah, I should also mention I found this really interesting because a lot of the actual subspace states are, you would say, kind of n-dimensional vectors because they have Hamming weight 1. And so the instant kind of pushback towards that is like with quantum machine learning, the whole what's the word? I can't think of the word right now. But what's so good about it in the loose sense is that you can exploit this exponentially large Hilbert space, but that's not exactly, at least superficially, it seems like they're not doing that when they're encoding n-dimensional vectors with n-qubit systems. And they even say that it doesn't look like it uses the quantum advantage offered by exponentially large Hilbert space. But then they note that the exponential size of the Hilbert space is instead leveraged to encode not only vectors as superpositions over bit strings of Hamming weight 1, which are just bit strings with 1, 1, but also it encodes all k-dimensional subspaces of Rn into superpositions of bit strings of Hamming weight k. And that's again, that's what kind of arises a lot of these quantum algorithms that they present along with this paper. So yeah, that's the other thing about this paper that I love, that it not only presented a new way to view quantum linear algebra and quantum computation, numerical linear algebra operations on quantum computing with quantum computers, but it also presented not one, not two, but three quantum algorithms using these subspace formulations. And I found that really interesting. So I'm just going to list them off because I still need to look over them myself. But one of them was determinant sampling. The second was singular value decomposition. But for compound matrices, since you're not dealing with vectors anymore, and compound matrices are generally they're matrices that act on subspaces instead of vectors individually. And the last quantum algorithm that they present, all with a theoretical at least speed up to that they claim, is on quantum topological data analysis. Which honestly, I have no idea what quantum topological data analysis is about, but I found it really exciting that they said that the new method operating on the subspace perspective gives a circuit depth reduction from O to O of n to O of log n. Well, that's an exponential depth reduction, right? Yeah, so this paper is crazy. What can I say?